Welcome to the session on line coding schemes. There are different conversion schemes: digital to digital, digital to analog, analog to digital, and analog to analog. The process for converting digital data into digital signal is said to be line coding. Digital data is found in binary format. It is represented internally as a series of zeros and ones. Digital to digital encoding scheme is shown in this slide. The input digital data is converted into digital signals via the encoding process. Line coding and decoding. In computers, encoding is the process of putting a sequence of characters, example letters, numbers, punctuation, and certain symbols, converted into a specialized format for efficient transmission or storage. Decoding is the process that is opposite process, the conversion of an encoded format back into the original sequence of character. Here in this slide, a encoder is available at the sender side and the decoder is available at the receiver side. The encoder receives the digital input and convert the received digital data into digital signals and transmitted to the receiver side. The receiver has decoder that converts the received digital signal into digital data and submit to the receiver. Digital to digital conversion using line coding. Data can be either digital or analog. Signals that represent data can also be digital or analog. In this section, we see how we can represent digital data by using digital signals. The conversion involves three techniques: line coding, block coding, and scrambling. Line coding is always needed. Block coding and scrambling may or may not be needed. Line coding is used to convert digital data to a digital signal. What is line coding? Line coding is the process of converting digital data to digital signals. Converting a string of ones and zeros into a sequence of signals that denotes the ones and zeros. For example, a high voltage level is indicated as positive volt, that could be represent a 1, and the low voltage level is considered as a 0 or negative voltage, that could be represent a 0. Characteristics of different line coding schemes. The first characteristics is signal element versus data element. A data element is the smallest entity that can represent a piece of information, that is the bit. In digital data communications, a signal element carries data element. The data elements, what we need to send; signal elements, what we can send. Data elements are being carried, signal elements are the carriers. The ratio represented by R is defined as the number of the data elements carried by each signal element. In this slide, you can see one data element per one signal element, that is shown in the first diagram, that occupies one clock tick. The second example, one data element per two signal elements transmitted. So the R value is 1 by 2. It occupies single clock tick. The third diagram shows two data elements per one signal element. R is equal to 2. Here, two data elements are occupied single signal element. The fourth one represents 4 data elements per 3 signal elements. R is equal to 4 by 3. Data rate versus signal rate. The data rate defines the number of data elements, that is bits, sent in 1 second. The unit is bits per second. The signal rate is the number of signal elements sent in 1 second. The unit is baud. The data rate is sometimes called the bit rate. The signal rate is sometimes called the pulse rate. The modulation rate or the baud rate are the other names. One goal in data communication is to increase the data rate while decreasing the signal rate. Increasing the data rate increases the speed of the transmission. Decreasing the signal rate decreases the bandwidth requirement. The relationship between data rate denoted by capital N and the signal rate denoted by capital S. So S is equal to N by R. The average signal rate is defined by S average is equal to C into capital N into 1 by R with a unit of baud, where C is the case factor. Mapping data symbols onto signal levels. A data symbol or element can consist of a number of data bits. Either it may be single element or two element. A data symbol can be coded into a single signal element or multiple signal elements. So the example is given here. It is from the range of -1 to plus voltage, otherwise 0 to negative voltage. The same way, -1 to positive voltage and or negative voltage, otherwise 0 to negative voltage to otherwise positive voltage. The ratio R is the number of elements carried by a signal element. Example, a signal is carrying data in which one data element is encoded as one signal element, that is R is equal to 1. If the bit rate is 100 kbps, what is the average value of the baud rate if C is between 0 and 1? Solution is, we assume that the average value of C is 1 by 2. The baud rate is then, as per the given formula, S is equal to C into capital N into 1 by R, results 50 kilo baud. Second example, the maximum data rate of the channel is N max, that is equal to 2 into B into log L, that is defined by the Nyquist formula. Does this agree with the previous formula for N max? Solution is, a signal with a L levels actually can carry log L bits per level. If each level corresponds to one signal element and we assume the average case C is equal to 1 by 2, then we have the following formula: capital N max is equal to 1 by C into capital B into R, that is 2 into B into log L. Consideration for choosing a good signal element referred to as line encoding. Baseline wandering. A receiver will evaluate the average power of the received signal and use that to determine the value of incoming data elements. If the incoming signal does not vary over a long period of time, the baseline will drift and thus cause errors in detection of incoming data elements. A good line encoding scheme will prevent long runs of fixed amplitude. Line encoding characteristics. First characteristic is a DC component. When the voltage level remains constant for a long period of time, there is an increase in the low frequencies of the signal. Most channels are band pass and may not support the low frequencies. This will require the removal of the DC component of a transmitted signal. Second characteristic is self-synchronization. The clocks at the sender and the receiver must have the same bit interval. If the receiver clock is faster or slower, it will misinterpret the incoming bit rate. The effect of lack of synchronization is shown in this slide. The first diagram shows the sent information. The second diagram shows the received information. The difference is the received signal not matching or synchronized with the given clock rate. Because of that, the lagging is shown in this second received signal. Example 4.3. In a digital transmission, the receiver clock is a 0.1% faster than the sender clock. How many extra bits per second does the receiver receive if the data rate is 1 kbps? How many if the data rate is 1 mbps? The solution is, at 1 kbps, the receiver receives a 101 bits per second instead of 1000 bits per second. So 1 bits per second is extra. At 1 mbps, the receiver receives 1001000 bits per second instead of 1000000 bits per second, that is 1000 extra bits per second. Line encoding characteristics. Error detection is another characteristic of line coding. Errors occur during the transmission due to line impairments. Some codes are constructed such that when an error occurs, it can be detected. Noise and interference. There are line encoding techniques that make the transmitted signal immune to noise and interference. This means that the signal cannot be corrupted. It is stronger than error detection. Line coding schemes. There are 5 schemes available in line coding. One is unipolar, second one is polar, third one is bipolar, fourth one is multi-level, and fifth one is multi-transition. So each scheme has its own techniques. Unipolar has non-return to 0, polar has non-return to 0, return to 0, and biphase, that is Manchester and differential Manchester encoding. Bipolar has AMI and pseudo-ternary. Multi-level has a 2B1Q, 8B60 and 4DPA-MS5 techniques. Multi-transition has MLT3 methods.